So welcome. My name is Ramon Morros, and I'm going to present you some results on face recognition. First, this slide has been created by Elisa Seirol, who was the, the person who the last year gave this module. Okay. I put some modifications. So this is a short idea of what I will show you. First, we will define what face recognition is, and we will look at some applications of face recognition. Then we will see the most popular databases for training face recognition systems, and we will see some of the principal works in the last years. Okay, making more attention to the more important algorithms in the field. And finally, I will present you some challenges that are still open in the face recognition field. So the applications of face recognitions are wide. Okay, there are a lot of applications. Most of them we are familiar with. For instance, payments. Nowadays, there are some applications for your mobile phone that allows you to use your face as an authentication system. Okay. Also for access and security, to access several places, you can use some sensors that record your face and decide if it's you or not you. And this can be combined with other with other methodologies, okay? Using two-factor authentication. For instance, you can combine your face with some key or some kind of card or password or code or whatever, and this way you can increase the security of the system, okay? If you don't want an extra security, what you can do is just drop the other modality and only use your face. That it's more convenient, okay? It's less cumbersome than entering a PIN or something like that, okay? But also there are other applications in automatic video indexing, for instance. Nowadays there is a lot of hours of video, and if you want to look in a huge database, in a huge video database, and do you want to recover something from this database, you need indexes, okay? And for these indexes, the identity of the person, it's very relevant. So detecting and recognizing the persons, the relevant persons that are in the videos, is very important for this reason. There are also applications in criminal identification, okay? For instance, if you read the newspapers, you will know that most administrations have efforts in this field, okay? In the FBI has a huge database of half the population in the USA, and also in China there is a wide deployment of security cameras, okay, to make surveillance of the population, okay? Another different type of applications, it's in advertising. Okay, in this case, it's not strictly face recognition, but some kind of face technologies where you can use the faces to identify, for instance, the age of the people, of the gender, and this can be used to target the advertisement, the ads, to the specific people. Okay, and finally, also in healthcare, there is a lot of applications trying to use this facial expression analysis, okay, for instance, to diagnose some illnesses, or also determine if a person is in pain or not and the degree of pain, and also some other efforts are to prevent the medication non-adherence, okay, to check if the people has taken the proper medication or not. Okay, so of course there are some applications that are very problematic from a privacy sense of view, okay, but there are others also that can be quite useful. Okay, so I leave you a couple of videos summarizing a little bit these applications. We have no time to look at the videos here, but you can take a look at home. Okay, I think they are quite interesting. Okay, so let's see a global overview of identification, the face recognition. Okay, so usually what you have is two different kinds of systems. Okay, we could classify in closed-set face recognition. In closed-set face recognition, you have a training database, and all the individuals that can appear at test time, okay, at the production time, do appear in this training database. So you are sure that there are no people outside this database. Okay, and there is also the open set face recognition. In open set face recognition, the system will be presented with individuals that were not available, that you don't have images at training time. Okay, this is the case in most real-world applications. Okay, for instance, if you are trying to find the faces in a video, for sure there will be a lot of people that are unknown and that appear only once, and you are not interested in annotating these people. Okay, so you can make models, you can have a database of several people that may have interest to you, but there will be hundreds, thousands of others where you don't have images at training time. But you have to classify these people as unknowns. Okay? So this makes the problem much harder, and the type of solutions are usually different. For the closed-set face recognition, you can use any classification approach. For instance, you can train a network, a BGG, or ResNet in a pure classification sense. Okay? And when a new face is entered into the system will output the most likely class, the most likely identity for this person. Okay? In an open set face recognition, you cannot do that. Okay? Because if you present a people that was not in the training set, the network will output an identity, okay? But it will be a wrong identification. So in this case, what you have to do usually is to use face verification. In face verification, the idea is that you extract some kind of feature vector and you compare with the feature vectors of the known people. Okay? And then using the distance between feature vectors, you can determine if this feature vectors corresponds to this person or to this person or to known at all. If the distance is too large, then you will the distance to all of the known person vectors, then you will decide that this person is not in the database. Okay? So for the classification problem, for the closed-set wall, it's enough to learn some separable features. You know that convolutional neural networks can be seen as producing feature vectors for the input images. Okay, so long as the feature vectors are separable, okay, then you can classify the input classes. Okay, but in the open set face recognition, this is not enough. You need to establish a margin, a large margin between the classes, okay, so that when unknown people appear, you can discard them because the features of the known people are very compact. Okay. So to train face recognition systems, we usually need large databases. Okay, there is a lot of people in the world, and if we want to differentiate between different people, we need training sets that have a lot of the identities. In the last years, there has been like an explosion of large data sets, okay, and some of them, for instance, and this Microsoft Celebrity 1 million, that contains 1 million different identities. And for instance, for the 100,000 top identities, there is 10 million images. Okay, so we have a lot of images to train the different systems. Okay, for instance, MegaFace also has almost 5 million faces using more than 500,000 different identities. Celeb faces, it's 10,000 identities, okay? There is also YouTube faces, faces scrap, and Cassia web faces, and BGG faces too. For instance, it's almost 10,000 identities with more than 3 million different faces, okay? All these, the problem with all these databases is that sometimes they are not disjunct, because most of these databases are created from celebrities, okay? And why from celebrities? Because celebrities are easy to mine. Most of these databases are created automatically by mining the internet, and most of them use, for instance, databases such as EMDB, that is a data set of a website for films containing information about the actors and so on, okay? So then you can collect images from here, and you know the identity of these persons. Otherwise, you have to supervise and put the identities by hand, okay? So the problem here is that most of these databases, okay, are overlapped. The people appearing in most of them is the same people, okay? So you just you cannot create a really huge database by agglomerating the different databases. You have to take into account that there are some repetitions. On the other side, you have, yeah. In the slide before or after? This one? Okay, so that is just an image to. Well, no, this is just put an image to decide if these people and these people are the same or not. So, yeah, you have to decide if they are the same or not. No, it's just to avoid a white space here. Okay. Sorry, I wanted to also to show you there is also other databases that are for testing. For instance, the leveled faces in the wild, or evolutions of that. Okay, so there is a commonly used databases, face databases, where the people test the systems. Okay, also the mega face and celebrity faces 1 million contain also testing splits for creating competitions and so on. Okay, so this an overview of the main contributions in the field. Okay, so it starts with using deep learning. It starts more or less at 2013 by the appearance of AlexNet, and the first systems were using, for instance, the AlexNet or BGGNet and so on as classifiers, okay, for closed set face recognition. Okay, at the same time, there are other works that use these networks, okay, for extracting feature vectors and then using some kind of applying for verification. Okay, then we will see how. For instance, DeepFace in 2014, FaceNet in 2015, and BGG Face. Okay, SphereFace in 2017, and BGG Face 2. And of course, these solutions are based on the basic classification networks, but used as a feature extractor. So let's start by the DeepFace architecture. Okay, so it's a work by 2014, created at Facebook, and it's a convolutional neural network with a particularity that some of the filters are not purely convolutional, are what is called locally connected networks, where that is some kind of special kind of convolutional network where the weights are not the same in every layer. Okay, in a given layer, at different positions, the weights can be different. Okay, and this is a powerful solution, but the problem is that as the localization is important, the images need to be correctly aligned. Okay, all the faces have to be correctly aligned. Okay, and this in real situations it's hard to do. Okay, in this work they try to frontalize the faces, so that convert the faces to a frontal view, and aligning them using the A's and the nose. Of course, this is only working for high-resolution images, because in low-resolution images, aligning, finding facial features, and aligning, it's quite complicated. Okay, and it's not always working. In this work, they use a convolutional neural network for feature extraction, and then for verification, they tried to use two different approaches. The first one was to use a weighted chi-square distance, okay, between features. In verification, you try to decide if two images are coming from the same person or not. Okay, so it's a binary response. So the idea was to extract the feature vectors for both images and then compare those images using some kind of distance. In this case, the chi-square distance. Okay, a weighted chi-square distance where these weights were learned by linear SVM. Okay. The other approach was to use a CMS network. CMS network, it's a solution that tries to perform metric learning. In metric learning, you try to generate embeddings that have the property of that the feature vectors are close in the Euclidean space for faces of the same person and far away for faces of different persons. Okay, so you learn the embeddings so that they fulfill this property. Okay, you can do that by duplicating the convolutional neural network, so the weights here and here are the same. Okay, so you have the two different images through the same network, and then there is an extra layer that tries to minimize this distance between the embeddings for the faces of the same person, and to maximize this distance from faces of the same person. Okay, so we are modifying the embedding so that they fulfill this property. Okay, and at the end, we have some feature vectors that are very compact for each class. Okay, so at the end, this is only for training, but at testing, you just extract feature vectors, and you compare these feature vectors using the Euclidean distance. And if the Euclidean distance is small, you decide that are from the same person, and if it's large, you decide that it's from different persons. Okay. Another approach in this same area is the FaceNet, that is using a triplet network. It's very similar to the CMS network, but in this case, you train the network by using triplets of images. Okay, so for each triplet, you have an anchor image, a positive image, that is an image of the same identity from the anchor, and a negative image, that is an image from a different identity from the anchor. Okay, so you have an anchor, a positive identity, and a negative identity. Usually, you will expect that the positive identity is closer to the anchor than the negative. Okay, so in some cases, this is not the case. If the feature vector, if the embedding is not working properly, so we try to modify the embedding so that this is true. Okay, using the triplet loss function. In the triplet loss function, we minimize this, that is the distance between the anchor and positive minus the distance between the anchor and negative, plus this alpha, that is a margin, okay, to make sure that we are separating even more the positive from the negative. That are the difference between positive and negative. Okay, so also as in the previous case, the network is the same. The weights are the same in the three versions of this network, and at the end we get a feature vector that is discriminative by using just an Euclidean distance. Another work is DeepID2. that it's also using a Siamese approach, but in this case it's combining the verification loss and an identification loss. Okay, the verification loss is the same loss that for the Siamese network. Okay, so it's something like that. Okay, so for the identities of the same, for images of the same person, we are minimizing the distance, and for the images of different persons, we are maximizing, because this is negative, also using a margin. This margin, it's a number that tries to separate more these cases. Okay, this is for the verification, and for the identification, the loss function is the cross entropy. Okay, and in this case, the training, it's combining both the identification and verification losses. In this case, also to improve the results, they use not only a detection of the face, but several patches, 25 patches. Okay, and for each patch, they extract a feature vector of 160 dimensions, and they concatenate these 25 feature vectors into one large 4,000 dimensional feature vector. Okay, this is because even though we have good face detectors, sometimes the alignment of the face detector is not perfect. Sometimes you correctly detect the face, but not exact. The detectors do not crop exactly the position of the face, and the algorithms are affected by this lack of precision in the cropping of the face. Okay, so by using several crops, they minimize this problem. In this case, also, okay, once we have the feature vectors, this DeepID2 uses a joint Bayesian model where each person, each feature vector is modeled in this way, like each feature vector is considered that there is a part that represents the identity and a part that represents the variations, intrapersonal variations. Okay, so if we have different images of the same person with different poses, with different expressions, okay, there is this part that represents what is intrinsic to the person, and this part is the small variation for changes in expression. Okay, this can be modeled during training, and using that probability distribution, it's possible to compute this log likelihood ratio test that will provide the final probability that two images are from the same person or from different persons. Finally, the last one that I will review is sphere phase. Okay, in the sphere phase, they realized that the softmax functions, in fact, it's having, or it's creating feature vectors that have some kind of angular representation. Okay, for instance, this is a toy example with two classes, and this is the feature vectors. This is painting the feature vectors in a two-dimensional space. See, as you can see, using the softmax, okay, the results are not very good for using these Euclidean distances. Okay, because a sample here and a sample here are more similar, they have a smaller distance. Okay, so interclass distances can be smaller than intraclass distances. For instance, this vector and this vector are from the same class, and there is a large difference between them. But if you see that, you will see that they are aligned in a more or less in the same angle. Okay, so here comes the idea of using the angle as a classificator. So ideally, I could put a frontier, a decision decision plane here, hyperplane here, separating the two classes based on the angle between the feature vectors. Okay? But if you try to do that using the angle to classify, softmax is not providing enough discrimination for this. Okay? So then the idea of the authors is to modify the softmax loss function by, in fact, the softmax loss function can be represented in this way, where this W and B are the weights and bias of the last fully connected layer. And then by making sure or constraining that this is 1 and the bias is 0, we have, and we can make sure for that in the training process. Okay, they have this modified softmax loss function, and for the modified softmax loss function, it can be seen that this modified softmax loss function is a little bit more discriminative, and if you project this in a sphere, okay, if you project the features in a sphere, okay, the angular separation is larger with this modified softmax function. Okay, so you can put an hyperplane separating based just on the angle. Then, by an evolution of that, you can use also to further separate the feature vectors, you can use a margin, an angular margin. Okay, so they try to increase the angle between the different representations by using this factor m, and in fact this can be done by using a loss function of this type, where this function is nothing else than an evolution of this cosinus here. Okay, and with this modified angular softmax, you can make sure that the features are much more discriminative and can be separated by using an angular, using the angle between the features. Okay, the effect of the margin of this parameter m can be seen in this plot. Okay, so when we are increasing the value of the margin, what we are doing is separating more and more the features of the different classes. Okay, and this is a projection into a sphere showing how the classes can be more and more separated by increasing this margin. And using that, well, they achieve quite very good results with much less training images. For instance, they are using wet phase that is using about 500,000 different images, and the best results it's from FaceNet that is using 200,000 million images for training. Okay, so it's much less. And this is important because training with 200 million images takes a lot of computational effort. Okay, to summarize, we have still some open challenges, okay, in face recognition. Nowadays, they are quite very good systems for face recognition, but there is still a lot of challenges. For instance, in the cross-pose face recognition, okay, if you have frontal images in your training set and then you try to test with profile images, then the performance is dropping quite a lot. Okay. Also, the age of the persons, it's a problem in systems from face recognition because we experiment a lot of changes along the time. Okay, and we are quite different when we are old, when we are young. There is also a lot of factors like makeup, scarves, and whatever, and other things that you can wear that are a challenge for face recognition. Another problem is illumination. Of course, if there is a really poor illumination, the usual systems cannot, the RGB cameras have a poor performance, so using near infrared it's sometimes an option, but then you have to train the systems for near infrared cameras. For low resolution, in a lot of cases you have a distant camera that can capture only low resolution images, and then most of the solutions here are quite difficult. And also photo sketch face recognition. Sometimes you can draw some lines and you want to check if using that you can to recognize people. Other problems that are for training, for instance, is the few shot face recognition. Sometimes you only have a few images to train a recognition system because you cannot collect more images, okay? Or 3D face recognition because there are a lot of problems with cheating the face recognition system. You can put a picture inside the face recognition system. So to avoid that, we can rely on other systems like 3D face recognition. The problem is that for 3D face recognition, there are not a huge data set with a lot of images. Okay, the number of images in 3D data sets is much smaller than for RGB images. Okay. Okay, and if you are interested in this subject, we have a small team with Elisa Sairol, and we are working mainly in open set deep learning at this moment, and we have participated in several challenges. So if you are interested, contact us because we will have something for you. Okay, any questions? So thank you.